morning, good afternoon, good evening. It's Stereo Police. Today I'm going to be doing a video, not so quick, but not such a quick video, but I've been wanting to do this for a while. I was discussing with a friend this very topic about selecting gear ratios based on increased or even decreased, but really mostly increased tire sizes, those of us who have trucks, basically. Could even be the same with cars as well, but mostly four-wheel drive trucks. And why you need to decrease your gear ratio, your final drive gear ratio, and why you need to do that with larger tires. And there's really a couple reasons. I'm going to go into that, and I'm going to start out giving you the quick formula, but that's not why I'm here. Anyone can run the quick formula for your new gear ratios to regain your performance and recalibrate your speedometer. But I think the important part here is not so much the quick formula. Anyone can do that. It's really the theory behind it, which is fascinating. And to me, as an engineer, I'm always appreciative of the theory. I want to know the theory. And any good mechanic just doesn't, a good mechanic, and there are lots of ones that are not so good, just parts replacers, but any good mechanic who really wants to know how to diagnose things needs to know the underlying theory. If you don't know that, you're never going to be a good mechanic, ever. You have to know how things work and why. And so that's why I want to make this video. Now, there are other videos out there like it, but none to the extent that I wanted to make it today. And not only that, I spent a good portion of my career teaching, not this, teaching electrical engineering as well as intellectual property law. And so I thought I'd use those skills to try to really teach this theory in a way that almost anyone can understand and appreciate. So let's dive right in and let's talk about the problem first. Well, actually I want to talk about some theory first and then the problem. And I promise you this, if you stick with me till the end of this, you'll gain a really, now obviously if you already know this, you don't need to watch it, but if you don't know this and you stick with me until the end, you'll gain a really good insight into not only the solution to this problem, but a lot of other aspects of automobile drivetrains as well. And many other things. Be very edifying, and I'll do my best. So we're going to break this up into several parts. The first is going to be 3 slides on theory, and then I'm going to discuss the problem here. And then we're going to go, and there's really 2 problems with increasing, and I'm going to go with increasing your tire size. That's typically what happens. You have a truck, get a lift kit on it, for example, and then you want to go from 29s or 30s to 36s, and all of a sudden, feels like you don't have much power. You're not accelerating that quickly, and your speedometer's off. It says you're doing 55 when you're really doing 63. So, not good. And there's a way to properly correct it. The way to properly correct it is not recalibrate your speedometer. Not at all. It's change your final drive ratio. So, we're going to talk about why and how. All right. There's only 3 slides on theory, and I just want to briefly discuss these things. First of all, and it's been a long time since I've had numerous physics courses, but this is going to be very basic. No deep theory here, but just to remind you that a force, and we're going to be talking about forces a bit today, and we're going to talk about torque as well and speed. But a force, without getting into mass and acceleration, just the basic concept of force is just a push or pull on an object. And you can see the little diagram here. This guy is pushing a big block, and he's exhibiting a force against that block. Now, whether or not the block actually moves is irrelevant. he's still, the block may move, and in that case, work is being done. If the block doesn't move, work is not being done, but nevertheless a force is being applied to the block, and the block is, by virtue of probably friction, it's providing an equal and opposite force, so the whole system is in equilibrium. So this is a pushing force right here. Of course, you could have a pulling force as well. Instead of pushing from this side, you can have this guy pulling. It's the same thing. It's just a force in a different direction. So forces have direction as well. They have magnitude. We typically in the U.S. measure the magnitude of a force in pounds. And they have direction. I mean, you could pull the block that way or that way. And of course, you have gravity pulling it that way. That's a force. And there's also a twisting force as well, like when you turn a screwdriver, or you have a ratchet turning a nut, and you have this twisting force, and that's going to be referred to as torque. And we're going to talk a bit about that. So let's dive right into torque. And this is really interesting. So we just talked about force. And just to give you an example, okay, that pushing or pulling a block is one thing, but what if you want to tighten a nut, for example, or a bolt on the other end, or a screw? We're going to be twisting. And certainly you have to apply a force to it, but it's not a linear force. It's not a force in a straight line. It's going to be, in this case, sort of a rotational force. So how do you do that? Well, in this case, the example is a wrench. Hang on just a second. Okay, I had something that was about to pop up on my screen. Let's see. Yeah, I'm recording. Good. Okay, so we have a wrench. And so where's the force applied? Well, the force is applied by your hand at some point along the length of the wrench. But the wrench is not going to go in a straight line exactly. It's going to make a series of turns. And that force is applied at a certain distance along the wrench. So here's a diagram B. So what's going to happen is you're going to get this twisting motion right here. And so the amount of force or twisting motion that's being applied to this nut right here is called torque. So I just like to think of torque as a twisting force. It's a bit different, but that's basically what it is a twisting force. Now the interesting thing about torque, though, is, again, we are applying force at a distance. Force at a distance. And the units, I mentioned before, the units of force is typically pounds. In fact, when you measure your weight on a scale, it's not really your weight. You're not measuring your mass, you're measuring your weight, and weight is a force. It's the force of gravity, wherever you're weighing yourself, pulling you towards the center of the earth. So you're measuring your force in pounds. That's what you're measuring. So when someone says go measure your weight, say, oh no, I'm going to go measure my force. That's what you're measuring. Anyway, which by the way would vary depending on how far away you are from the center of the earth. Gravity weakens the further we get away from the center of the earth. But anyway, but by a minuscule amount based on the surface of the earth and elevations and such, but it does. Now, let's talk about this wrench real quick, and this is interesting. Let's say, and I've run some numbers right over here. Let's say we have this guy right here at 1 foot. Guy, gal, doesn't matter. At 1 foot, applying 1 pound of force to tighten this nut right here. Okay? Well, the torque, real simple. 1 foot, 1 pound of force. That's 1 pound-feet of torque that's being applied. It's being applied as a twisting force. 1 pound-feet of torque. What if we applied 2 pounds right here instead of 1? Well, that would be 2 pound-feet of torque because we're still at 1 foot away. Now, what if we went over here and we applied the original 1 pound, but now we're 2 feet away? Okay, 1 pound at 2 feet is 2 pound-feet of torque. What if we were to apply 2 pounds of force at 2 feet away? 2 times 2 is 4. That's 4 pound-feet of torque. So this is basically a lever. It's a lever. And the further, given the same amount of force applied, the further you get out on the lever, the more torque you'll apply at the expense of rotating by smaller and smaller increments. But basically this is the action of a breaker bar. More torque. That's why they're long. Much more torque given the same amount of force you can apply with your hand. Except that lever's got to be really long. Alright? Also, to the contrary, and this is really interesting, let me see if I can find a quick way to erase this stuff right here. And this is super important. I guess this video is going to be longer than I thought. And this becomes really important to the video today. Alright, but it'll be well worth your time. Alright, look at all that. Look at that mess. I wasn't prepared for this. I started getting in, speaking, and I'm already on a tangent. Okay. Okay, this is draw. Alright. Let's do the opposite. Let's say that whatever, this is an axle right here, and it's turning. So the axle itself is applying torque. Okay, there's no hands out here. Forget the hands. All right. The axle is applying torque. And let's say the axle is applying 10 pound-feet of torque of twisting motion, a twisting force right here, okay? So let's say that we go 1 foot out, and we want to measure, with a scale, how much force is being applied right here. Well, it's quite the opposite. The further we go out, okay, the most force we're ever going to get applied on any given point here is closer in. Okay? The further we go out, okay, the mechanical advantage decreases. Okay, before, when we were actually applying force out here, we get a mechanical advantage as this lever increases. Now it's going to be the opposite because the driver is now the axle. So let's calculate it. We've got 10 pound-feet of torque at 1 foot away. So how many pounds are going to be applied of force right here? Okay, 10 pounds. All right, so 10 pound-feet equals 1 foot times X number of pounds. Take 10, divide it by 1. We get pounds, 10 pounds. Let's take that same 10 pound-feet of torque and go out 2 feet and have some kind of scale right here to measure the amount of force being applied. We're 2 feet out. Well, 10 pounds equals 2 feet times X number of pounds. Bring that 2 over, divide it into 10. Now we have 5 pounds. So the further we go out, the less and less force will be measured at any given point on this lever. That's when the axle itself is doing the driving. So it's the opposite of when we're actually using a lever to apply torque. It's the opposite. All right. Hope that makes sense. If not, go back and watch it and run the numbers. One more thing. Gear ratios. And then this is the end of the theory, then we're going to move into the problem. I want you to stare at this just for a second. And that's why I like to take pauses. I want to stop and think if I missed anything. Real quick, going back to this example. This right here is a good analogy of increasing your tire size. Right here. If this was your car axle and this is your smaller tire, okay, you would have, and this is the road surface. Now let's go down here. That's the road surface, and that's the road surface. And you had, which is a very low number, but typically have a lot more. But you had your axle providing 10 pound-feet of torque here, with this particular tire size right here, which has a 1 foot radius. 1 foot radius. You would have a road force of 10 pounds. And of course, friction would be in this direction. That would, assuming the wheel's not slipping, friction is what propels you forward. Would be equivalent to that 10 pounds as well. So you'd have 10 pounds of road force. You get a larger tire size right here, this big one, okay, twice the radius. Now we have a 2 foot radius, just like we measured. Now all of a sudden, our road force is 5 pounds. That's the amount of force that's going to be applied to the road to propel you forward. So by doubling our tire radius, we've halved the amount of force that's going to be on the road to propel us forward. You see the problem. Now it's rare if ever we ever double the tire size. Normally we go from like a 30 to a 36. It's not even near doubling it, but I guess it's possible to do that. So that's the problem that causes the apparent power reduction. I say apparent, it's not a power reduction. Horsepower never changes. But what changes is the amount of force that's actually applied to the road when we increase tire size. So basically it reduces our ability to accelerate from a stop. So it's going to reduce our acceleration basically. And of course also, and I'm going to get into this in a minute, a larger tire size has a larger circumference. So for every rotation of the drive shaft, we're going to go a longer distance. And given that the speedometer is essentially geared to the drive shaft, so it's going to take your speed from basically the drive shaft speed. Well, if for every rotation of the drive shaft we're traveling a larger circumference, which this circumference becomes a linear distance on the road when the wheel spins, then we're going to be going a further distance, meaning our actual road speed will be higher than what's indicated by the speedometer. So, for example, your speedometer might read 55 and you might be doing 63. So that's the problem with larger tires: reduced road force, lack of acceleration, and increased road speed per the speedometer reading, resulting in an uncalibrated speedometer. Now, this final theory slide, I'm not going to look at this here. We're going to look at reduction gears. Gear ratios are given as the driven gear divided by the drive gear. This is the gear being driven. This is the gear doing the driving. So it's basically, you could call it diameters. It's a diameter ratio, which is the number of teeth ratio as well. Or the radius ratio. Doesn't matter. So in this case, there are 10 teeth on the drive gear and 20 teeth on the driven gear. So the ratio is 2 to 1. When you see final drive ratios in a car, you'll see 3.23. You'll say it's a 323 or a 311 or something like that. Well, all they're giving you is the first number right there, because the second number is always going to be 1. Okay, so just keep that in mind. It's always to 1. To 1. All right. So what happens here in a reduction gear situation? This is overdrive. I want to talk about that. Almost all the gearing in our car are reduction gears. Almost. So what happens is two things with respect to gears. Number one, When you have reduction gears, we have an increase in torque with respect to the driven gear and a decrease in speed. That's the trade-off. We can increase the torque if we decrease the speed. So just for an example, let's say that right here in our drive gear, we have 100 pound-feet of torque. Okay, right, on the axle of the gear, at the pivot point. Well, let me just use random units right here and just say that this is a diameter of 1, and this is going to be a diameter of 2, whatever it is. Let's call them feet. That's a rather large gears. It could be anything, centimeters, but it doesn't matter. They're gonna cancel out. And that also coincides with the number of teeth. So this has 10 teeth, that has 20 teeth. Still the same ratio, 1 to 2. Doesn't matter. But let's look at it in terms of torque. So if this gear has a drive torque of 100 pound-feet, we come out to actually where the teeth apply the force. Actually, the force is heading down, isn't it? So here's a force heading down this way. So we need to convert twisting torque to linear force right here, because this tooth right here is going to push down on that tooth right there. Well, how do we do that? Well, it's real simple. We have 100, excuse me, 100 pound-feet. We just divide by 1 foot. Okay, and we will get 100 pounds of force applied from the drive tooth to the driven tooth, right there. Now, let's talk about ultimately the amount of torque that this gear is going to possess. Okay, now we know the force that's applied to this tooth. It's going to be the same. It's going to be 100. But we know the distance to the pivot point or to the axle. It's 2 or 2 feet. So 100 pounds times 2 feet are 200 pound-feet. So we just doubled the torque. So basically gears are like a series of levers. Basically, you can look at each tooth as a lever. Each tooth is a lever. And just run torque. Run your torque numbers. It's that simple. It would be like, like this. That's a bunch of levers on your drive gear. And here's a bunch of levers on your driven gear. You have torque and you have distance. It's really, really simple. Now, that's an increase of torque. Okay, it's a ratio of 2 to 1. And that 2 to 1 will basically be your increase in torque ratio. But remember, that comes at the expense of a speed reduction. I'm not going to erase this, sorry for the mess. So think about it this way intuitively first. This has 10 teeth. This has 20 teeth. If this rotates 1 full revolution, that means 10 teeth have gone around. Only half of these teeth, only 10 of these teeth have gone around, which means this is only rotated 1/2. So 1/2 speed reduction. That's simple. So if this is being driven at 100 RPMs, this is going to be driven at 50 RPMs. So that's our trade-off. Increased torque, decreased speed. That's it. And of course, with gears, the direction of rotation changes too. So, when our drive gear rotates this way, our driven gear rotates that way. So we do have a change in rotation. If we needed to have the same rotation, ultimately, we'd have to have another gear out here of the same number of teeth to switch that rotation back to where we wanted it. So it'd be a 1-to-1 ratio. That would be if. Okay, let's get into the problem. Okay, with an increase of tire size, think about your truck now, going from 30s to 36s, let's say. As I mentioned, we're going to experience a decrease in road force, meaning poorer acceleration. It's going to be very noticeable. Also, you're going to experience a higher ground speed for the exact same drive shaft rotation. The speedometer will always read low. It's going to read low. In this, so what can we do to fix it? Okay, we've increased our tire size, our diameter or radius, depending on what, however you want to look at it. Well, we can't re-gear our transmission. Our engine's fixed. So there's only one thing we can do. And we have these final drive gears back here. And these can be adjusted. These can be changed to compensate for the increase in tire size. And that's what we're going to be talking about today. Now, if you want to stop here and not learn the theory behind it, which I think is fascinating, there's a real simple formula. Old tire diameter to new tire diameter times the old axle ratio will be the new axle ratio. All right, so I'm not going to run the numbers here, but it would be basically, now remember, new to old, so it would be 36s divided by 30s times 3.23. Well, let me see what it says. I'll just do it while we're here. 36 divided by 30 times 3.23, 3.88. So to compensate for that increase in tire size, bring your speedometer back into calibration and regain the same amount of road force, we need to reduce these gears, to lower this gear ratio to 3.88. And even though the number is higher, remember this was 3.23 to 1, and now we're going to go to 3.88 to 1. So let me just draw this real quick. Okay, so that means, okay, these are the same. That means we need to have a larger driven gear. Because remember, this is a higher number. We need to increase our torque to regain road force, and we need to reduce our speed. We need to reduce our axle speed for the same revolutions of the drive shaft. So this is actually a lower gear, even though the number is higher. Because remember, the ratio is the driven gear to the drive gear. All right, so that could be the end of the video right there if you wanted, but that doesn't show you the whole. I want to give you the whole theory based on the whole holistic approach here. All right, let's talk first, and let me give you an example about road speed, and then we're going to get into road force. And this is the interesting part of the whole thing. Now, I've decided, this is kind of awkward, there are many ways to demonstrate this, but I've decided to demonstrate it in a way that I think makes the most sense. Because your speedometer is going to be taking readings off basically the drive shaft speed. Now, there may be other variations of this, but let's just pretend in this example your speedometer is calibrated by taking readings off your drive shaft speed. We want that because remember, if we took it off somewhere up here, well, these gears are constantly changing. These rotations are constantly changing when the gears are shifting. And also, if we took it off of engine speed, well, engine speed is going to be the same, while drive shaft speed varies based on what gear you're in. So engine speed wouldn't be a good indicator. What's a good indicator basically is drive shaft speed. So, and this speedometer is calibrated. Okay, there's a gear in there that calibrates the speedometer to road speed based on what your final drive ratio is and based on your stock tire diameter. It knows these things, and with that, it's basically a multiplication factor, a number, a gear ratio that says, hey, if this drive shaft is spinning this many revolutions a minute, I know this ratio, I know this tire size, I know, which means I know the circumference of the tire, then I know the ground speed. And it doesn't change. Not going to change. So let's look at it that way for a second. So let's look in this example, and I'm going to choose for every 3.23 revs of the drive shaft, we have 1 revolution of the axle in this example. That's because that's what our final drive ratio is. So every time this pinion gear revolves 3.23 times, the ring gear revolves once, meaning the axle revolves once and the tire revolves once. Okay, and this is ignoring any differentiation. Okay, the car's moving in a straight line. But it even works, I want to get on a tangent, it even works through differentiation. Remember, when you're going around a turn, your outer wheel is going to go faster and your inner wheel is going to go slower. But remember, the way differential works, these speeds, okay, the amount that the outer wheel speeds up is identical to the amount that the inner wheel slows down, because velocity can't disappear. This ring gear, okay, this ring gear is attached to the pinion, and the pinion is attached to the drive shaft. This ring gear is going to rotate at a certain speed depending on the drive shaft. Velocity can't disappear. So when you go around a corner, this outer faster wheel, the velocity has to add up, okay? Has to add to the speed of the, or subtract, I should say, because this is going to go lower, this is going to go higher, this will go lower, negative. These two are going to have to add up, or subtract up, basically, to equal the speed of the ring gear. So it doesn't matter if we're going around a corner or not, but we're not going to pretend we're not going around a corner. Pretend we're going a straight line. All right. Now, we know that if the tire is 30 inches, this is your old tire, 30 inches in diameter, the circumference of the tire, which means the distance all the way around it, the circumference for 1 revolution, is going to be, and this is pi times diameter, is going to be 94.2 inches. So for 3.2 revolutions of the drive shaft, we're going to get basically 7.85 feet of linear travel. Okay, remember that. I'll come back to it. Now, let's go to a 36-inch diameter tire. Same thing, same final drive rate. We haven't changed anything. We got a bad truck now. We have a flawed truck. Okay, so for 1 revolution, okay, for 3.23 revolutions of the drive shaft, we are going to be traveling 113 linear inches, which is 9.42 feet. 9.42 feet. Now I want you to remember, the reason why I chose 3.23 revolutions of the drive shaft is because that's where the speedometer is attached. The speedometer is dumb. Speedometer is looking at the drive shaft. Speedometer thinks everything's the same. Speedometer doesn't know you change tire size. So speedometer says in these two scenarios you're going exactly the same speed. Except you're not. Because before you change the tire, for that many revolutions of the drive shaft, you traveled 7.85 feet. After you traveled 9.42 feet, meaning you're going faster. Not by an insignificant amount either, by a pretty significant amount. That's why your speedometer is out of calibration if you did not change the final drive ratio. Okay. Let me hit pause right here and we'll pick up. Okay, let's talk force reduction now. Road force reduction. If you like cars, you're going to like this. Let me give you an example, and this is a vehicle that I own. I own a 1985 Dodge W150 4x4. It has a 318 V8. Produces approximately 300 at the engine, 305 foot-pounds, 2,500 RPMs. I'm going to use that as a baseline to start the calculations here. That's the engine torque. Now, the gear ratio, and I'm gonna just start. I can choose any gear. I can choose a 1-to-1, but I'm just going to choose first gear because that's how we start accelerating from a standstill. So a lot of times we're in an off-road situation. We're in first gear. It's when we need the most. That's the most torque we're going to get, unless I'm going to ignore the transfer case right now. Let's just say we're in two-wheel drive. But it all comes out the same. So the ratio of the first gear in the transmission that I have is 4.56 to 1. So based on what we've talked about, there's a 4.56 torque increase. And, of course, speed reduction. But we're interested in torque right now. We don't care about speed. Okay, so that means the torque output of the transmission in first gear is 305 times 4. It's 1391 foot-pounds. It's quite an increase in torque. Of course, it comes with a corresponding decrease in rotational velocity or speed. We're also going to ignore, in this case it says there's a clutch in here, but even if it was an automatic transmission, you'd have a torque converter, and torque converters actually almost double your torque when you're taking off from a standstill, and eventually that torque multiplication goes down to 0 as you're cruising, but we're going to ignore that. It doesn't matter. It all still comes out the same. The effect is the same. So let's ignore torque converter torque multiplication, which sometimes is on the order of 2 to 1, on the order of plus or minus a half. Okay, so now we have our torque on our drive shaft in first gear of 1391. Here's our final drive ratio, 3.23, which is not atypical for a standard quarter-ton truck. So what's going to be our axle torque? Well, once again, we have a reduction gear. So we're going to increase torque again, decrease speed again. So axle torque is going to be our 1391 from the drive shaft multiplied by 3.23, so 4493. A lot of torque. We're going to ignore differentiation, but I will say, like we mentioned before, you go around a corner, outer wheel spins faster, inner wheel spins slower. We mentioned that before. Velocities have to add up. Okay, velocity can't disappear. Well, torque can't disappear either. And the way an open differential works is it's going to split the torque between both tires, the faster one and the slower one, with the majority of the torque going to the wheel spinning the fastest. And that's why an open differential will easily get you stuck in a mud puddle, because it's going to send the torque to the wheel with the least amount of traction. That's just the way it works. And that's the need for lockers and limited slips and others. Okay, that's a topic for another time, but the torque will split as well. And also I will note that open differentials are fantastic, and don't ever think that they're bad, because when you're cornering, you want most of the torque to go to your outer wheel because it actually helps to push you through the curve better. It helps to, if you look at the vector, it actually helps to push you through the corner better. Whereas if you were sending the torque to the inside or the slower wheel, it would push you, the vector itself would push you out of the curve. It would work against you. So open differentials are basically what you want when you're on a dry road and you're cornering. So this is a good thing. And I'm on a tangent. All right. So we have 4493 pound-feet of torque to the axle. We're going to ignore differentiation. Now, let's get to the force part of it. We have our 4493 right here. That's our axle. But that doesn't mean that that's the force. Okay, torque is our spinning force, but the force where the tire meets the road is a linear force. It's not a spinning force. So we've got to convert our spinning force to a linear force, and we've already talked about that. We could look at the tire as a gear if you want to, although it's not, but it kind of is. And we can look at this, and like at the very beginning when I used that wrench example, okay, we're not applying, we're actually taking our spinning force and coming out at a distance and measuring the force. And so the further the distance, the less force we're going to get. Okay, the further we come out. We talked about that earlier. That's why larger tires will produce less road force. But let's calculate the road force here. And it's called force applied. And of course, if this wheel was lifted off the ground, there'd be no force applied because there's nothing to work against. You have to push against something, and that's friction. That's the equal and opposite reaction. So friction is actually what causes you to move. All right, but we don't care about friction today. We care about applied force to the road. So with our 30-inch tire, which has a 15-inch radius, okay, now we have our torque and we have a radius. Now 15 inches is, I'm going to put this in feet. We have to keep our units the same because our torque is measured in foot-pounds. 15 inches is 1.25 feet. So the force applied to the road is our 4493 divided by 1.25 is 3,594 pounds. 3,594 pounds. That's a lot. Now remember, this is first gear. We're taking off from a stop. That's when we need the most force to get us moving. That's the most we're ever going to have. As the transmission shifts into higher and higher gears, this amount of road force is going to go down. All right. Now, let's see what happens if we increase tire size. Now we're going to go to a 36-inch tire with an 18-inch radius, which is 1.5 feet radius. What's the force applied? Well, it's our same. The torque doesn't change. Okay. 4493, that doesn't change. That's at the axle. Doesn't change. What changes is the diameter. Okay, we went from 15 inches to 18 inches. So again, that's 1.5 feet. What's our force applied to the road? 4493 divided by 1.5, 2995. What was it before? 3594. So that's like 500 some, almost 600 fewer pounds applied to the road. That's not insignificant. That's why you notice that you're not accelerating as fast. It's 500 fewer pounds of force applied to the road just going up from a 30 to a 36. In this scenario, given the gear ratios and given the first gear transmission ratio. How do we fix it? Again, that's I just ran the number. It's a 16.7% decrease in applied road force with the larger tires. 16%, almost 17% is not insignificant. You're going to feel it. All right. So how do we compensate for it? Well, we're not going to go in and change our transmission gears. That would be insane. We're not going to do anything to the engine. Propeller shaft doesn't do anything. The only thing that we have to alter is our final drive ratio. And as we know, said it before, if this is our old ratio, how do we increase torque to increase that force? We need a larger driven gear. The driven gear is the ring gear. The ring gear. And that larger ring gear is going to do two things for us. It's going to increase the torque and the speed. It's going to decrease. So that's going to compensate for both of our deficiencies at the same time. All right, at the same time. So remember, initially I ran that real simple equation, new tire divided by old tire multiplied by the gear ratio to get your new ratio. But let's do it the long way, just to see exactly what's happening. So I've got my 36s on there now, and let's see exactly what's happening here. And this is the fascinating part. This decreased my applied force to the road. Now initially I still have right now my 5243 foot-pounds of torque here. Well, how do I increase the applied force to the road? I need to increase the torque on the axle. That's the only way to do it. And so I want to increase the applied force back to what I originally had, my 3594. So you remember it went down to 2995. So I want to increase this applied force to 3594. Okay, how do we do it? Well, let's do everything in reverse. So, what we do, here's our 3594, and we know we have a distance of 1.5 feet right there to the pivot point or the axle. So what torque do I want here to get that road force? A simple multiplication, 3594 times 1.5. I need a new axle torque of 5391. So from this to this. Okay, 5391. I need a new axle torque. 5391. How do I do it? Increase the ring gear, meaning lower the gear ratio. That's how I do it. So, let me hit pause here just for a second. I need to get a sip of water. Okay, doing a lot of talking, so get a little dry. All right, so we know that the torque we want here is our new 53. Let me just come down here. It's our new 5391. We also know if the drive shaft, we have the same torque we always had, 1391. Well, that's easy. That's easy. Our 1391 from the drive shaft times our new ratio will equal 5391. So we just simply divide, and we get 3.88. So 5391 divided by 1391. Okay, our output is 5391 divided by our input, 1391 torques, will give you 3.88. So we went from 323s up to 3.88s. Now, and that's going to give us back to something very close or exactly to our original road force. Now the thing is, when you do this, is you come up with this theoretical number, but in practicality, they only make so many final drive ratios for your vehicle. Just to give you an example for my Ram, here's some typical ratios that are made for them. So I'm going to have to select from what's available. So what you do is you take the 3.88 and go to the next highest number or the next lowest ratio. So 3.88, that's not good. That's 3.92 is the next lower ratio. Higher number but lower ratio. Lower gear, I should say. Lower gear. 3.92. It's pretty close. It's a good fit. It's the next lowest gear that's available to me. 392s. And if you remember when I ran that original quick calculation, it came up with 388s as well. I just did it the long way to show you. So I'm going to select my 392s and pop them in there. My 392s, pop them in there. And we'll be A-OK. With 392s, it's going to be almost identical on speed. And it's a slightly lower ratio than 388s, but not by much. And you'll get your original road force and maybe a little tiny bit more. And your speedometer will only be off by a smidge, nothing to worry about. Probably off by the width of the needle, you know, if you have a needle, unless you have a digital speedometer. I have an 85, so I have a needle. So yeah, that's how that works. And that's it. And that's the theory of it. So we regain our road force, and we reduce our speed by equivalently. All right. So let's take this was our final drive ratio of 323. Here's 392. Let's run a couple numbers here. Look at what happens with respect to speed. Let's go back to speed now. So if you remember, with our original ratio, 323s, every 3.23 revs of the drive shaft, we travel 7.85 feet. Okay? And when we went to our 36s, for every 3.23 revs of the drive shaft, we traveled 9.42 feet, hence we were reading low on the speedometer. Now what happens? So for every, and there's a number of ways to do this. I kind of did it the long way, but for every 3.23 revolutions of the drive shaft, and again, that's because the speedometer is connected to the drive shaft, so I want to keep this equal. Okay, now we have our 36-inch tires. All right, so 3.23 revolutions, 36-inch tires for one rotation of the axle, 113 inches. However, with the new ratio, remember before, for every 3.23 revs of the drive shaft, we're going to make one revolution of the axle. Now, with our new ratio, for every 3.23 revs of the drive shaft, we're only going to make 0.82 revs of the rear axle. Remember, it's going to get slower because the ring gear got larger. So we've slowed down the axle. So that 113 inches of travel before the new gear ratio, we're just going to multiply by 0.82 to get 7.73 feet for every 3.23 revs of the drive shaft, which is almost identical. Very close. Basically 7.85, 7.73, almost identical. The distance traveled per revolution of the drive shaft. So that's how we fixed the speed problem, and we've also fixed the ground force problem. It's all done. And we've, again, 392, that was, it's a little off because I picked a standard ratio that was available, and that's what you're going to have to do. So actually, what's going to happen in this scenario with our new ratio, traveling just a little bit slower, so the speedometer is going to read just a smidge fast, which is good. You won't get a speeding ticket. And we'll get a tad bit more ground force because we selected the next lower ratio, not the next higher. And there you go. I hope that makes sense, and hope you enjoyed it. And that's the theory of it. Torque, speed, gear ratios, and what's actually going on when you pop some larger tires on that beast. One thing I'd really like to discuss in the future, if I have the time, there's so many myths. I used to talk a lot about audio equipment and stereo equipment. There's so many myths in the automobile industry, and so many myths I'd love to discuss. One of them is exhaust scavenging. There's so much BS out there about that, and you know what effect it has and how much of a difference it makes and how to handle it and deal with it and make it work for you. And there are other very really interesting, obscure, esoteric, arcane topics that I'd love to hit in the future. So I hope you enjoyed this. Stereo Police over and out. Ciao.